Okay, so question number 12 says, a toy gun shoots a 20-gram ball with a spring constant of 12 newtons per meter. The spring is going to be compressed 10 centimeters, and it wants to know, first off, what's the speed if the ball leaves the gun without any friction, and then if there is a frictional force of 0.05 newtons, what is the speed when the ball leaves the gun in that circumstance? So, some things that I'm just going to change. We know that the mass is 20 grams, which is 0. Let's go 1, 2, 3, 0.2 kilograms. We know that the K value is 12 newtons per meter, so that's fine. It has a displacement or a delta X of 10 centimeters, which is 0.10 meters. And then we have the force of friction, which would be 0.05 newtons. So, we're getting all our values into our SI units here to be able to not worry about plugging them in later on. So let's look at our scenario. Right here we have elastic potential energy is greater than 0, so that's some value, and then we don't have any other energy, so that's what we have there. When the ball is leaving here, it's at the same height, so there's no change in gravitational potential energy, but it does have now kinetic energy, and then the potential energy would be 0. So what would our energy equation look like, right? So the first thing we're going to do is we're going to find V final, and that's going to be elastic potential energy initial equals our kinetic energy final. So that's 1/2 K delta X squared equals 1/2 mv squared. My 1/2s are going to go away. I'm going to divide each side by m. My m's cancel out, and I'm left with v squared equals K delta X squared over mass, square root both sides of those. So that's going to be K times 0.01 squared divided by 0.02 square root. That's going to come out to be the square root of 6, which is about 2.45 meters per second. So that's how fast it's coming out when there is no friction, or without friction. And then it's going to be the same thing with friction. So with friction, now my equation is going to be, okay, I have elastic potential energy. I'm going to lose some of that energy due to work done by friction, and that's going to equal my kinetic energy at the end, right? The frictional force in this case would be opposing the motion. So if the ball was here, there'd be some frictional force pushing backwards. And so let's figure that out, right? So we have 1/2 K delta X squared minus the force of friction times the displacement equals 1/2 mv squared. We can't cancel out the 1/2s here just based on the fact that we don't have 1/2 everywhere, so I'm going to divide this side by 1/2 m by 1/2 m. That's going to cancel that side out, and then I'm going to be left with velocity squared equals, so really dividing by 1/2 is the same as multiplying by 2. So that's going to be K delta X squared minus 2 force of friction times my displacement divided by my mass. So that's 12 times 0.1 squared minus 2 times 0.05 times 0.1 divided by 0.02. And actually, sorry, I forgot to square root all of this to find V. That's going to end up being the square root of 5.5, which is going to be about 2.35 meters per second. And again, that should make sense, right? Initially we had a velocity of 2.45 without friction. We should have a little bit slower with friction because we lost some of our energy to that friction, right? And so you might say, well, what's happened to that energy, right? Well, with frictions, that ball has heated up a little bit due to friction, or the tube that it went through is heated up a little bit, so that potential energy has been converted into thermal energy. And so while our energy hasn't been destroyed, it's just been converted into a different form.